So let's talk about length matching. I'd like to be able to route like this without having to do any add length on the shorter one of the two, just to make it easier. So what I'm going to do is I'm going to make sure there's two signals cross in what I call the straight parts of the waveform. And that what that will do is minimize the amount of jitter I see, which is movement in time from bit to bit of where the crossing is detected. And so what I'm going to do is look at the fastest edge at the receiver, figure out what the time interval is between, so if those two tick marks are lined up, I'm okay. If it crosses like this, I still detect that there was a crossing. However, from bit to bit, it'll jump around a lot, and that will be lots of jitter. So I want to stay like this. So figure out what that is in time, convert it to distance using your E sub r data you saw earlier. Here is a piece of math I did. The LVDS standard, which was written by National Semiconductor, says you can, because it's fairly low data rate, you can have a arrival time difference of 400 picoseconds, which is about 6 centimeters. You know what it says in the guidebook? It says you have to match to 100 mils. So when I see a number like 100 mils, I know that's made up. So in the case of LVDS, we could be that kind of error, or mismatch would be okay at 2.5 gigabits per second, 150 mils. So for the numbers I heard you all say here, you could have a length mismatch of 100 mils with no problem at all. The rates I heard you talk about. But this is an example of how you figure out what the number is. Now, I know that you're going to have no trouble routing to 100 mils all day long, because that's no problem. That isn't where the problem is going to come from. It's going to come from the glass weave. You'll see that later.